we start with the introduction of truss systems. Okay, so it's a very important what we call systems, or what we call here particularly on engineering structures, or for mechanical designs, in our mechanical designs. Okay, so we see how we formulate it and the fundamental of it using FEM methods, and how we solve it, then compare with later on ANSYS. All right. So a truss is an engineering structures. Consists of straight members connected at their end by means of it could be pin, rivets, weldings, bolts. Okay, so something similar like this. So the member in trusses systems, it could be any materials, steel, aluminum tubes, wood, okay, wooden strut, metal bars, angles, and also channels. Okay, different types of channels. So this truss system is a practical solution for many structural problems. So you can see it in our, daily life. This truss system exists in like power transmissions towers, the bridges, even the roof of the building itself, the crane itself also are part of the truss systems. Okay, so here we focus more towards plain truss. So plain truss is a truss whose member lie in a single plane. So something like this. Okay, if you could also go a little bit more complex, what we call here 3D, or what we call here space truss. So where you have a three-dimensional basically truss system. So a lot of time it can be analyzed in plane truss or so, okay, in a single plane itself. So here we call it a plane truss because the force acting on this truss it basically lie on this particular plane itself. Okay, so we call this plane truss. So members, when we said this is the truss system, then they connected by joints. Okay, these are the joints. So these are the members. So these members could be any types of material, steel, aluminum tubes, wood, metal bars, or whatever. Right? So these are members. So these member generally basically two force members. So undergoing axial, you'll see that is undergoing axially loaded. When I have a load applied at here, so okay, at the joint, usually when we are uh, considering truss systems, okay, the force or the load are usually applied at the joints. Okay, so at the joints here, then you have the reactions, the support at the joints here also. So when you have applying a load, for example, a displacement truss, then you will see that each member of them is actually two force members. So you have these two members undergoing compressions, and the bottom one undergoing tensions in this case. Okay, so you see these things. Okay, this member, or this member itself are actually axially loaded. Okay, we are saying that you are in tensions, or you are in what we call compressions axially along that particular so-called member itself. So, of course, these internal forces are act in equal and opposite directions along the members. Okay. So we need to do some assumption also when we do analysis of trusses. Okay, the members we have to assume that it's connected by a smooth pins. Okay, or by a ball and socket joint in three-dimensional truss. So if you have a three-dimensional truss, basically we want to say that this whatever the load that you applied, okay, it will go towards the member itself later on, the internal forces. Okay, because of the two force member, so no losses over there. So that is the assumptions. The first assumption. The second one, you have to be what we call, it will be intersecting the joining member will intersect at the common point which is the pin or joint there. So, okay, so trusses with welded joint may be also treated as having smooth pin with no bending. So that is a keywords here. So when all these truss systems that you have seen here, okay, so when you have applying loads at the joint here, okay, so it is only undergoing these two force members which is axially loaded or either in compression or in tensions, and this particular member itself, there are no bending. Okay. So they are connected at a joint, okay, at the smooth pins, okay, no bending happens. Okay. So all loads must be applied at the joint of these trusses, so that the majority of the load is applied at the joints. Okay. So what it means here, all the loads, okay, applied at the joint, so it's taken by that particular joint itself lah. Then that is the key assumptions, okay, for a truss system. And the weight, it can be negligible. So weight of the member itself, let's say the bar, the metal bar itself, or whatever aluminum tube itself, these members, the weight of this member itself can be ignored or can be negligible. Okay, because usually when you compare to the applied loads, it is far more smaller, or it's not significant compared to the applied loads. So it could be negligible. But in the case of you want to consider, also can, then what we are doing is we consider half of the weights, okay, of each member is applied to the connecting joints. Okay, so for example, sorry, here, so if we want to consider, we are saying that this particular load itself, okay, compared to the weight itself, okay, is far more very very large, okay, than this W itself. Okay, so not significant the weights, okay, of these members. But in the case of we want to consider this weight, so probably you have to consider this mg. Okay, so here you have your load plus mg over 2. Okay, here also at here you have this mg over 2 at here. Okay, both of the joint will share a so-called two the weights, right, at here. So that is what it means lah. Right? If the weights of the member are to be considered, then half of the weight of each member is applied to the connecting joints. So remember, right? So here, for truss system, we are assuming that the load is applied at the joints. Okay, the supports or everything, the boundary also at the joints, and the member are not undergoing any bendings. Okay, it's purely axially loaded. So that is some assumptions. So how we formulate it, right? Again, it is axially loaded member, just that you have a different, basically it's subject to a different angles, right? When you have a plane truss, then in order to formulate it, of course, we can use the direct formulation that we have discussed in the introductions, right? Or the energy methods that we have discussed in last week, axially loaded axial members, okay, they are same. Okay, so again, it come back to this F equal to Kx, and F, our K itself is this AEOL lah. Okay, so it's basically the similar things. So it's a centrally loaded members lah, okay, and it's undergoing a uniform cross sections. So here our K is basically AEOL. All right. So how we start to formulate these things? So here we are introducing, we are using two coordinate systems. So two frame of reference are required here, because you know that just now, if you see that, for example, this particular truss system itself, okay, a 3 nodes or 3 point itself, right? So when you have a load applied here, then this thing sitting with a certain angle. You see that it come with a certain angle. This come with a certain angle, right? And this member also it lay down horizontally with theta equal to 0. Okay, so we have to consider the so-called angle, and we have to transform it to the correct coordinate systems. So here we use two frame of reference here to describe the truss problem. A global coordinates and local frame reference. Okay, global coordinates and local coordinates. Okay, so if we choose global coordinate systems. Okay, you still remember our global coordinate system coming in is the capital X here, also Y, because it is not no longer in one direction or one direction in either X or vertically either Y. Okay, so it could be any. So you have X and Y coming in. So here we use this X and Y global coordinate system to represent the location of each joint. Okay, so if I have a point at here, okay, then I have my Y, I have my X. So I know, okay, let's say this is my or let's say this is my origins. So I know where is my X and Y, where is my X and Y and here, okay, where is my X and Y, okay, at here, where is my X3, Y3 at here. Okay, so that basically to represent the location of each joint here, referring to the nodes and keep track on the orientations of each members. So we have each member, we have these elements, we have the elements, one nodes, okay, two nodes connecting element. Here we have, let's say, for example, we have three elements. So we know the orientation of the elements, like what I mentioned to you, okay. Under this coordinate Y and X itself, then where is the nodes positions, okay, and how it's being transformed, okay, at what angles, theta 1, theta 2, then here is theta 3. So we know that. So it helps us to keep track on the orientation of each members lah. So we have the angle of theta. Again, uh, we have we use it these global coordinates to apply constraint. Okay, we know where to apply constraints. Okay, at here, at node 2, or let's say this is node 1, this is node 2, this is node 3. At node 3, we know that, okay, node 3 is x3, y3. So we know that where we should putting the constraints, okay, which is at here, the constraints, support, and the loads. Okay, we know where to put it. Okay, all in a global coordinate system. Okay, of course, later on when we solve it, okay, we also find our displacement, okay, our displacement or deformation undergoing these particular loads, okay, in this particular coordinate system like x and y. So global x and y, we know that this particular node itself, I mean how much it deformed in terms of x and y global coordinates, and also here in this particular node 3, where is how is the displacement, okay, in terms of x and y. So here we use xy to represent the locations, okay, the position of the nodes, the orientations, and where to apply the constraint, the loads, and also to represent the final displacement of each joint or each node, okay, in the global directions. Okay, so that is mainly on that. We also need a local coordinate systems, xy. Here we are referring to lowercase xy to describe a two force member. If you still remember, we have a member at here, a member at here. Okay, so all are going this, let's say, in tensions or in compressions. These are having in what we call their own so-called coordinate system, which is a local coordinate system in probably uh, x and y. Okay, so here we also need a xy local coordinate system to describe these two force member and behavior of each individual members lah. So we want to look into the deformation of each individual members. Okay, then only we can combine them into in deformations uh, that created in each node itself, okay, in global coordinate. So that's why later on you see we combine these two coordinate system and we build relationships between these two coordinate system, and easily we can transform from a local to global, global to locals. Okay, so let's have a look on it. So let's start with the formulations. Just now we have this F equals to K equivalence, or what we call the AE over L, right? We have this so-called K equivalent equals to AE over L, right? So it's axially loaded members, okay? For each of them, in the truss systems, each member are also all axially loaded, just that it comes with a certain orientation or angles. Okay, so the global displacement here, of course, we have this U in X and Y directions. So if you are looking into this X and Y global, okay, so each node itself, we have this X and we have this Y, okay, node I, okay, X displacement and Y displacement. Node J, also we have this X and Y displacement, right? Then again, for this member itself with an orientations of theta. So let's say this member itself is not laying down like this, okay, horizontally or vertically, but it's with a certain angle of theta. Okay, then we know that this particular member itself will undergoing either in tension or in compressions along its member, along this particular member itself. Okay, so along this particular line itself. Okay, so we will say that it will be having its displacement also, okay, along this u here along the member itself. Here we put another coordinate system, which is along the member is x, okay, perpendicular to that member itself is y, right? So this is local coordinates, local displacement x and y, right? So to build the relationship between the global displacement and local displacement, so if you can look into uh, this itself, right, for one coordinates, for one node itself, so if I want to find node I, the displacement at x for node I, so I have the local coordinates, local displacement at x, okay? So I have sorry. So I have UIX here. It is cos theta. Okay, it's going so-called like this, going in the vector. So then we have okay, another one minus, okay, u, this is also theta, this is also theta, then u minus u I y sine theta. Okay, so that give us the relationships of uh, uh, global, okay, and local displacement. So similarly, okay, with the displacement at j, so-called not j, not I, it's not I, but y directions. Okay, all right. Then we have here is the positive and positive lah. So it's these two line. Okay, so it's going up and going up. Okay, sine. One is sine theta, one is cos theta. So I have u I x sine theta plus u I y cos theta. Okay, so that gives us these two equations. All right, but then for node J itself, also the same. Node J, I mean in x direction and in y direction, also will give us the similar equation, just that I now is become J. Okay, so if I can put them in a matrix forms, then I have this global displacement actually equals to uh, a matrix, a matrix which is this one, okay, multiply with my u, okay, so I can have my u ix iy jx jy equals to a transformation matrix here, multiplied with u ix. So basically now I have a u UIX equals to cos theta UIX, okay, local displacement, then negative sine theta UIY, okay, then plus 0 plus 0. Then UIY, I have sine theta, okay, so I have sine theta and cos theta, all positive, right? So that gives us this equation and these equations, right? So to transform it into matrix, okay, then that will be it could be represented by this, okay, U, okay, that is the relationship between a global displacement and local displacement, okay, U equals to TU. So this T we call it at a transformation matrix, okay, cos negative sine theta, cos theta. So for the node I, for node J, then we have cos negative sine theta, cos theta at, right? So this T is a transformation matrix that allow the transfer of local deformation to their respective global deformation or global values, okay, or displacement. All right. So if you have the displacement can be transformed from local to global, then your force itself also the same, can be transformed from local to global, okay, using the same transformation matrix. Okay, so if you look into this, okay, just now you are in displacement. Now if I have in the force itself also the same lah. So my force, okay, in the local and global coordinates, that can be transformed using the similar transformation matrix. Okay, so that is the relationship between local and global matrix, either in force or in deformations. Right. Then if you look into each particular member itself locally, then we know that, okay, in a matrix forms, this particular member itself, we know that F equals to Kx, right? Okay, K dx, or K equivalent dx. All right, and in terms of if you can write in terms of locals, local coordinates, then we have this K U. Okay, so here for one members, okay, for one member, two nodes, okay, undergoing with theta like this, okay. But then in local coordinate, it is along this member. So you will see that all displacements is along its x-axis lah. Local displacement, okay, local displacement in x-axis only. So you don't have any displacement in y. So if 4 times 4 matrix, okay, two nodes, two direction x and y, so it become a 4 times 1, okay. So you have this UIX, UIY for node I, UJX, UJY for node J. Same with the FIX, FIY for node I, FJX, FJY for node J. So and it only happen, your K itself is happen at the what we call the x-axis of this local displacements. Then we have this K. So if you rewrite it, then you have this Fix equals to K UIX minus K UJX. Okay, or we can call it K UIX minus UJX. Right? Then FIY is nothing. Okay, it's 0. So that's why you have nothing. FJX also the same. Okay, uh, when it go axial loading. Okay, then have what we call this K negative K UIX plus K UJX. So you end up also K UJ so-called X minus UIX. Okay, so that basically give us the two force members. So if you remember, okay, previously, I mean, either our axially loaded member is without any orientation, either in vertical or in verticals, okay, or in horizontal. We have our matrix F, okay, F I F J, okay, equals to K negative K negative K K U I U J. So it's similar. You see that? Just that now we because you undergoing some orientation, so we have to consider X and Y. But in this case, in local coordinate or local displacement, UIY is 0. Okay, UIY and UJY is 0. No displacement, local displacement in the y-axis because everything is undergoing axial loading. Okay, so it's either in tension or in compression along the x-axis. Okay, so you will see something similar like this, right? But then now you have you are basically uh, uh, decompose it into x and y direction. In this case, our y directions is 0. Okay, our y direction is 0, but we have to include it also. All right, then we look into this. Okay, if we want to write in matrix form, then we have this F equals to KU, right? Right, and just now we have the relationship between the local and global force, F, okay, equals to transformation matrix F, right? So if you can, we can make use of this. F itself, right, is TF. Then if I want to find, if I can find the inverse of T, okay, multiply with my F equals to inverse of transformation matrix, okay. Transformation matrix multiply with the T, multiply with this F itself, then this is the I. So I have T inverse F, okay, global equals to F, right? So if I have F, this one, it can be replaced by T inverse F, all right? Then equal to KU, right? Similarly, our U itself, local U, okay? Local U also can be represented by T inverse global U, right? So substitute everything in here, okay? Then here give us the relationships, right? Of our so-called force in, you see that here is in global coordinates. Okay, so how to find this T inverse? So T inverse here is actually same with, let me show here. So this T inverse, okay, is actually equals to T transpose because these are what we call orthogonal matrix. So whenever you have orthogonal matrix, this T inverse equals to T uh, transpose. So in other words, you actually don't need to find the inverse. Okay, you can get the transpose of this transformation matrix that it will give you the similar results, right? So just now we have this, right? T inverse multiplied with F equals to K T inverse multiplied with U, okay? So we have a T inverse multiplied with F, okay, equals to what we have here is uh, K T inverse U, okay? We have this K T inverse U, okay, which is the global, right? So if you want to rearrange it in terms of a global, if you want to rearrange it in terms of a global coordinates, K, U, okay, then we multiply pre-multiplications, okay, with T itself, right? Then we have F equals to T, okay, K T inverse U, okay. So that thing itself, okay, this itself is our K lah, okay, our K in uh, here is referring to its global, okay, elemental stiffness matrix. Okay. So how to find this K? Basically, it's a T multiplied with our initial K for transform matrix, multiplied with the inverse of what we call the transpose of the transpose of our transformation matrix. All right. So from a local coordinate systems, okay, F, okay, equals to K U. Okay, now we have moved to global, okay, which is F capital, so okay, global force matrix equals to T K T inverse here is actually equals to T transpose, right, U. Okay, so that gives us the relationship between the Bifrost, the elemental stiffness matrix, and also the global deflection or global deformation or displacement, okay, of the nodes of any elements. Okay, here we are talking about one elements, okay, two nodes. Okay, so that where we consider the theta coming in. So how to find this? Basically, if you can get the transformation matrix multiplied with the K multiplied with the transpose of the transformation matrix, that give you this lah. So this is our so-called K elemental, okay, in a global coordinates system.